right, here's our video today. So on one side, we have E equals PC. And then on the other side, I'm sure you know this equation. It's probably the most famous equation in the world from Einstein. E equals mc squared. And by the way, both of these equations come from the same equation from Einstein. And we'll break it down. And so if we start with E equals mc squared, we know this comes from the theory of special relativity in 1905. So let's get our pen ready. What should we use today? Maybe we'll use white. So in 1905, a long time ago, Einstein, he wrote the theory of special relativity. And what he's saying here is very simple. Well, it's not simple, but in simple terms, mass and energy are different forms of the same thing. So let's write that. Mass, how much matter you have. Mass and energy are different forms of the same thing. That's what he's saying here. So in other words, we can add more to it. Let's add more to it. They can change into each other. They can change into each other. So that's the simple definition of the theory of special relativity for this equation, E equals mc squared. And like I said before, this equation here on the left is part of it also. And we'll talk about that, break that down. And by the way, when he was using energy in 1905, at first, he didn't use E like we use today for energy, makes sense. He was using an L. And L stands for, well, it comes from an Italian mathematician, and it stands for Lagrangian. So I'll write that down, Lagrangian. That's a term we use for kinetic energy now. Lagrangian. All right. And so what Einstein used was, he was saying mass equals Lagrangian energy, right? Divided by c squared, which is the speed of light. So let's break down the equation on the right first. E equals mc squared, and then we'll do E equals pc. So let's get a clean page here. All right, and maybe we'll stick with white. Or maybe we'll go red. Why not? So just going back to Lagrangian, just so we understand that. So if you say Lagrangian now, like the L for Lagrangian, it's T minus V. And what it's saying here is it's the total kinetic energy. And kinetic energy is the energy of movement, the energy inside you, internal energy, we can say that. The total kinetic energy of a system. And I have other videos on this. So T is the kinetic energy, right? And V is potential energy. So that's where Lagrangian came from. But let's look at what we came here today. We'll look at E equals mc squared first. And like we said before, E is for energy, M is for mass, and C means the speed of light squared. Right? Put a little parentheses there. Got a little blurry there. And the speed of light, by the way, is 186,000 miles per second. It's extremely fast. Nothing goes faster than light. And if you snap your fingers, just snap them. Go ahead, snap your fingers. See, I just snapped my fingers there. When you do that, just to give you an idea of how fast light is, it's going around the world 7 times in your snap. 7 times. It's amazingly fast. 186,000 miles per second. So let's get the full equation here, because remember I said in the beginning, this is just part of the equation. It's not the full equation. So I'll use purple over here to put the full equation in. So and by the way, the reason why we use c for the speed of light is it comes from Latin celerity, which means just basically swift. That's what it basically means. So on his full equation, this is how he had his full equation. It's e squared, so hopefully we can fit this in, equals mc squared, right? The power rule here, right? Power to a power. Plus, here's that pc squared. So that's the full equation, and from that, we get this simplified when we're talking about certain things, which we'll talk about, right? So again, we know this part, the m is the mass, the c is the speed of light. This p over here is momentum. That's momentum. And of course, when you're moving, you're gathering momentum. So let's just use math now to break this down. Right? If we just wanted to solve for e, not e squared, what can we do here? Well, first of all, let's write this out, clear it out here. So if we do a power to the power, we're going to have m to the second power and c to the fourth power. Right? And then this would be p to the second, c to the second. Just remembering your exponent rules. Now, if we're talking about an object, let's say, an object that is not moving. Now, if an object is not moving, it has no momentum. Write it over here. If an object is not moving, now, of course, we did talk about kinetic energy before, and it has movement inside of it. But on its own, if it's not moving, if an object is not moving, it has no momentum. So if it has no momentum, P equals 0. And if P equals 0, if you look over here, here's my arrow, 0 times anything is 0. So that just cancels out. And you'll be left with E squared equals M squared C to the fourth. This would just cancel out, be gone, because 0, again, 0 times any number will be 0. Now, how do we get E equals MC squared? Well, it's a little math. Remember, if we square root both sides of the equation in algebra, if we square root them, the square root of E squared is E. And the square root of M squared C to the fourth will just be MC squared. And that's how we get it. Now, if you're unfamiliar with square roots, I'll just basically show you something here. You know, if we did the square root of 25, for example, well, that's plus minus 5, right? Because 5 times 5 is 25, right? Or negative 5 times negative 5 is 25. If I said the square root of 5 squared, well, we know 5 squared is 25, so that'll give us the same answer. And the square root of E squared, well, it's E because E times E is E squared. And when we had the square root of C to the fourth, well, we know it's C squared because C squared times C squared is C to the fourth. So you should know your exponent rules. I have videos on that if you need to understand that. So we came up with this because if an object is not moving, it has no momentum. Now let's look at the other equation. Rewind if you need to. I'm going to clear this out. And let's write the other equation. Let's change the color. There we go. A little blue today, brighter blue. And dark blue. And we'll use white. So remember, in the equation, the other equation, we said E equals PC. And remember, P is momentum. And when we're dealing with this equation, it's about light. It's all about light. Let there be light. And again, it's not just visible light. Remember, there's other light out there. Radio is light. Microwave is light. Infrared is light. And we can't see that light. And of course, there's visible light, and there's ultraviolet. That's light. X-rays are light. And gamma rays are light. So it's all part of the electromagnetic I'll write it over here, the electromagnetic spectrum. Right? That's light. And light has no mass. So let's write that down. Light, and we're talking about light, we mean photons. What happened over there? I don't know what happened there. Photons have, pen's a little breaking up on me today, have no mass. They have no mass. So let's write the full equation like we did before. We said E squared equals mc squared squared plus pc squared. Now, if it has no mass, guess what cancels out? What do you think? This cancels out because no mass is zero. 0 times anything will be 0. So you're left with E squared equals pc squared. Now, E squared equals p squared c squared. Remember the law of exponents. And then we just square root like we did before. Square root both sides, and we're going to have E equals pc. And that pertains to light. Now, by the way, just to add to this, just to understand what he was saying here, remember we said is like mass and energy are related. They're interchangeable. They can be changed into each other. And if you can take the energy inside you, for example, inside a human being, if you can make every atom, all the atoms into energy, which is very hard to do, you need extreme pressure and extreme temperatures. And remember, we have 7 octillion atoms inside of us. Well, you may know that, or maybe you don't. So let's think about this. Let's clear this out for a minute. 7 octillion atoms in you, in the human body. 7 octillion atoms. Let's put 7 octillion atoms in the human body, or more. And so if you can release that energy, that would be 1.86 kilotons of TNT, dynamite. And to show you how much that is, the atomic bomb in World War II in Hiroshima, or Hiroshima, however you want to pronounce it, that was 21 kilotons. Look how much more energy is packed inside you. Now, if we take a smaller object, which a lot of people use this, they use a paper clip. If you can take all the energy from a paper clip, all those atoms from a paper clip, you'll get 18 kilotons of energy. Very close to the atomic bomb in Hiroshima. So that's basically what those two equations are trying to say. All right.